Okay, so now we continue with inductor in the AC circuit L. Okay, so the circuit also known as a pure inductor circuit. Okay, so circuit of pure inductor consists of an AC generator and also inductor L. Okay, and the voltage across the inductor is known as VL. Okay, so the graph, sinusoidal graph for the current and voltage through the inductor in pure inductor circuit. Okay, as you can see here for the blue graph, it is represent the graph for the current, AC current in the circuit. Okay, and I0 is equal to the maximum current in the circuit, and for the red one, okay, the graph for the voltage across the inductor. Okay, so as you can see here, the voltage graph is graph of cosine. Okay, and then the V0 is represent the maximum voltage across the inductor. Okay, next we look at to the phasor diagram that represent the direction of the current and the voltage in inductor circuit. Okay, the blue one is the direction of the phasor diagram for the current. Okay, as the graph for the current is a sine graph, so the direction of the current will be towards the horizontal or to the right. Okay, while for the voltage, okay, since the graph is a cosine graph, graph of cos, so this one is VL, voltage across the inductor. The direction of the phasor diagram will be pointed upward. Okay, the current flows in the AC circuit is I equal to I0 sine omega t. Okay, just now we can see that the graph of the current is represented by the graph of sine, right? So that's why we get I is equal to I0 sine omega t. Okay, next, when the current flows in the inductor, the back EMF caused by the self-induction is produced and given by, okay, back EMF. Back EMF is denoted by epsilon B. Okay, so the induced EMF will be equal to negative L di over dt. Okay, and since I is equal to I0 sine omega t, so next we substitute. Okay, so the back EMF or EMF induced will be equal to negative L d over dt I0 sine omega t. So here we will differentiate the equation of the current, which is I0 sine omega t to t. Then we will get back EMF or EMF induced is equal to negative L I0 omega cos omega t. Okay, in a pure inductor circuit, the supply voltage V, okay, must be equal to the back EMF, okay, epsilon B. Epsilon B just now is also equal to the voltage across the inductor. Okay, but the back EMF will always oppose the supply voltage. Okay, as we got from the previous slide, okay, back EMF is equal to negative L I0 omega cos omega t, right? Okay, this negative sign indicates the direction of back EMF is always opposed the supply voltage. Okay, but the magnitude of back EMF and the supply voltage are equal. Okay, so that's why we get, okay, V is equal to back EMF, which is equal to L I0 omega cos omega t. Okay, so cos omega t, okay, then we transform into sine. Okay, into sine, we also get the equation that is equal with cos omega t, okay, which is equal to L I naught omega sine omega t plus pi over 2. Okay, cos omega t also equal to sine omega t plus pi over 2. Okay, then V naught. V naught is the maximum voltage, also equal to L I naught omega. Okay, so when we substitute L I naught omega here is equal to V naught, so we also get the equation of V, voltage across the inductor, will be equal to V is equal to V naught sine omega t plus pi over 2. Okay, the phase difference between V and I. Okay, how to get the phase difference? Okay, so we have to relate with the equation for the voltage and also current in a pure inductor circuit. Okay, equation for the current, I is equal to I naught sine omega t, isn't it? And then for the voltage, V is equal to V naught sine omega t plus pi over 2. Okay, so the phase angle is here. Okay, omega t for the current, okay, for the current from the current equation, and omega t plus pi over 2 from voltage across the inductor. So for the phase difference, so we have to minus the phase angle. Okay, this one is omega t plus pi over 2 is the phase angle for V, okay, minus the phase angle for the current, which is omega t. Okay, then we have to cancel omega t. We will get a phase difference, which is delta phi is equal to pi over 2. Okay, what does it mean? Okay, it means VL leads I by pi over 2 radian. Okay, we also can see from the phasor diagram. Okay, phasor diagram for the voltage across the inductor is pointed upward, isn't it? Okay, VL, and then the phasor diagram for the current is in horizontal. Okay, and as we know that the phasor diagram is a vector that is rotating anti-clockwise. Okay, so here we can see that VL is leading current by pi over 2 radian or 90 degrees. Okay, next, the inductive reactant in an inductor. Okay, inductive reactant is the resistance. Okay, resistance in a pure inductor circuit. Okay, resistance caused by an inductor. Okay, so that's why we get XL. Okay, inductive reactant denoted by XL. Okay, XL is equal to VRMS over IRMS, equal to, in terms of maximum voltage and current, we also can write V naught over I naught. Okay, since V naught is equal to L I naught omega over I naught, so I naught and I naught can be cancelled off, so we will get XL will be equal to omega L, and since omega is equal to 2 pi f, okay, so that's why XL also equal to 2 pi FL. Okay, inductive reactant XL is directly proportional to the frequency. How you can see the relation between XL and frequency? It is from the equation of XL. Okay, XL just now is equal to 2 pi FL, right? So that's why XL and frequency are directly proportional. Okay, directly proportional. So we can sketch a graph of impedance against frequency. Okay, for the inductive reactant, since it is directly proportional, so we will have a straight line graph. Okay, proportional graph. So this one is represent the graph of impedance against frequency for inductor. Okay, so now let's have a look to the summary on resistance, reactant and impedance. Okay, so the first one, okay, look at to the definition for the resistance. Resistance, the symbol is R. Okay, so all of you I think already familiar with resistance, right? Okay, what is the definition for the resistance? It is an opposition to alternating current flow caused by resistance, okay, in AC circuit. Right, opposition to alternating current flow caused by a resistor. Okay, next we have reactant, X. Okay, reactant, it is the opposition to AC flow caused by inductance or capacitance in an AC circuit. So reactant can be divided into two. Okay, the first one is capacitive reactant, which is XC. Okay, the definition for capacitive reactant, it is an opposition to AC flow caused by capacitance in an AC circuit, or opposition due to capacitor. Okay, the equation for the XC, okay, XC is equal to 1 over omega C, and also equal to 1 over 2 pi FC. Okay, next we continue with the inductive reactant, which is XL. Okay, the definition for XL, it is an opposition to AC flow caused by inductance in an AC circuit. Okay, for the inductive reactant, it is the opposition due to inductor. Okay, and the equation for inductive reactant, okay, XL, which is equal to omega L, and omega is equal to 2 pi F, so that's why XL is equal to 2 pi FL. Okay, the last one, impedance. Impedance, and the symbol is Z. Okay, capital letter of Z. Impedance is the total opposition to AC flow. Okay, total opposition here may be due to resistance, capacitance, and also inductance. Okay, so impedance, you may find impedance in the circuit which is consists of combination of RL, okay, RC or RLC circuit. Okay, just now previously we just learn about the pure inductor, pure capacitor and pure resistor, right? Okay, later you also find the combination circuit, which is RL, RC and RLC. So for the combination circuit, you'll find the total opposition, which is impedance Z. So in order to find impedance, okay, the equation for the impedance will be equal to square root of R squared plus XL minus XC squared. Resonance in RCL series circuit. Okay, RCL or RLC series circuit. So resonance can be found in a circuit that is consists of the combination of resistor, capacitor and also inductor. Okay, so look at to the definition of the resonance. Okay, resonance is defined as the phenomenon that occurs when the frequency of the applied voltage is equal to the frequency of the RLC series circuit, okay, which is F supplied voltage is equal to the frequency of RLC circuit. Okay, so the using of resonance, okay, it can be used for tuning a radio receiver. Okay, so now look at to the graph of impedance Z against frequency F for RLC circuit. Okay, for the combination of the resistor, inductor and also capacitor. Okay, so firstly look at to the graph of the resistance. Okay, here we can see that the resistance just have the horizontal graph, so it means that the value of resistance is not affected by the frequency, right? Okay, next the second one is the green one. Okay, graph of XC against frequency. Okay, XC and frequency are inversely proportional. Okay, from XC is equal to 1 over 2 pi FC, right? So that's why XC and frequency are inversely proportional. So that's why we have a curve graph. Okay, the blue one. Okay, the blue one is the graph of XL against frequency. Okay, equation for the inductive reactant, okay, XL is equal to 2 pi FL, right? So that's why XL and frequency are directly proportional, so we get a straight line graph. Okay, the pink curve represent the graph of impedance against frequency. Okay, the graph shows that at low frequency, okay, at low frequency means here, okay, at this area, at low frequency the impedance is large. We can see that the value of impedance is large, right? It has the larger value of impedance because of it is contributed by XC. This one is capacitive reactant. Okay, impedance is large because of capacitive reactant is large. Okay, at high frequency, at this area, okay, the impedance is large because of omega L. Okay, because it is contributed by the value of impedance is contributed by the inductive reactant. Okay, at resonance. Okay, at resonance, impedance Z is minimum. Okay, impedance is minimum, which is equal to R when at resonance XL is equal to XC. Okay, at this position, at this point, we can see that the intersection of inductive reactant and capacitive reactant, it shows that XL is equal to XC. At this point, resonance is occur. Okay, at resonance, XL is equal to XC, right? So the equation for XL is equal to 2 pi FL and XC is equal to 1 over 2 pi FC. Okay, so FR is the resonant frequency. So now we are going to derive the equation for resonant frequency. Okay, from this equation, we may find the resonant frequency will be equal to 1 over 2 pi square root of LC, okay, which is FR is known as resonant frequency. Okay, from the equation of the impedance, Z is equal to square root of R squared plus XL minus XC squared, okay, which is at resonance, XL is equal to XC. Okay, so when XL minus XC, we will get 0. So that's why Z will be equal to R. And at resonance, the opposition of the current flow to the circuit is minimum. Okay, when the opposition of the current is minimum, so we will get the maximum current through the circuit, okay, which is also equal to I RMS equal to V RMS over Z, and since Z is equal to R, so it is also equal to V RMS over R. Okay, so this equation just for only at resonance.